Science on Surfaces.
Welcome to this podcast. Today we will talk about superhydrophobic surfaces. We will talk about what a superhydrophobic surface is, what makes this property arise, and how superhydrophobic surfaces can be manufactured. Here with me in the studio I have Susanna Laurén. She is an expert on surface-related phenomena, for example adhesion, wettability, surface tension, and surface-free energy. Susanna has been working at BioLin Scientific around these topics for over 8 years, and before that she did her PhD on microfluidics and superhydrophobic surfaces. Welcome.
Thank you.
I'm really looking forward to learn more about this fascinating topic.
Yeah, good.
Yeah. So what is a superhydrophobic surface?
So simply put, they are surfaces that can repel water very efficiently. So superhydrophobic surfaces were actually discovered from nature. So lotus leaves have this property. And you might have heard a lotus leaf effect, which means the surface cleaning or the self-cleaning property of the lotus leaf. So basically, if you have a raindrop on the lotus leaf, it can just roll off the leaf easily. But if we think, in a scientific way, how we define superhydrophobic surface is that the water contact angle is about 150 degrees. And then it has a low contact angle hysteresis, and typically it has to be below 10 degrees.
What is the contact angle hysteresis again? A quick recap.
Yeah, so basically, if you place a droplet on a surface, you can measure the contact angle, and that contact angle is static contact angle. And so then, depending on which type of a surface you have, that the water drop can take different shapes. And in the superhydrophobic surfaces, it will be almost spherical. So the static contact angle will be really high. As I mentioned, it has to be higher than 150 to be superhydrophobic, but then it also has to, but it can be much higher than that as well. But this static contact angle is really dependent on how you place the drop on the surface. So basically the droplet can take a little bit different energy state, as we call it. So we have actually local energy minimums and local energy maximums. And the difference between those values are contact angle hysteresis. So if we take a little bit more, it's maybe easier to understand visually, in a sense that if you place that drop on the surface, then you start to tilt the surface. And typically at some point the droplet will start to move or roll off the surface. And when that happens, you can measure at the front edge of the drop. You can measure one contact angle, and at the back edge you can measure the other.
Right.
The front is advancing, what we call advancing contact angle, and the back is receding contact angle. So the difference between those two is the contact angle hysteresis. So basically the contact angle hysteresis almost kind of measures the stickiness of the water to the surface.
Yeah. Okay, and what value did you say that you wanted?
So to be super hydrophobic, that value has to be lower than 10 degrees.
Okay.
Because you can actually have very high static contact angle, but then you can also just tilt the surface and the droplet will not move.
Yeah.
So then that kind of loses, then you don't call it super hydrophobic anymore, because then all the things that you want to achieve with that surface are, they are not working anymore, because you don't have that.
Okay, so why are these surfaces interesting?
So there are actually so many different possibilities with this type of surfaces. So the water repellency is of course obvious one, and it's also quite easy to to think where you would want that, like in outdoor clothing, for example. You want to have, you have your typical raincoats, but they are not very comfortable if you want to run, for example. So you want to have fabrics that are comfortable, but then they can repel water as well. So then you could have different type of textiles that have this super hydrophobic property so that they repel water more easily. And then also different type of, anti-fogging windows, for example. You can imagine that would be a great benefit in
or
many...
even just glasses or
absolutely, like lenses.
Lenses.
Yeah, exactly. That would be a really nice property if you are wearing eyeglasses. You know that it's so annoying when you get that. Then I already mentioned briefly the self-cleaning property. There are other ways to achieve self-cleaning than superhydrophobic surfaces, but in lotus leaves the superhydrophobic surface, the water droplet rolls off the leaf, taking dirt away from the leaf.
So it collects all the dirt that it will pass.
Exactly, and all kinds of pathogens as well. So if you have like fungi or algae accumulation on the leaf, so it will also take away those. So that's kind of beneficial for the lotus leaf to have that kind of a property.
So where does this property come from then?
So basically there are two things. You have to have a proper surface chemistry and then some type of a roughness. So surface chemistry is some type of a polymer coating, typically like fluoropolymer coatings or waxes or things like that have very high or very low surface free energies. So contact angles on those water contact angles are very high. But even if you take some fluoropolymer coating, which has basically the highest possible water contact angle that you can find, if it is completely smooth, you can only have, let's say, 120 degree contact angle.
Which is not enough.
No, it's not enough. So basically then chemistry itself doesn't explain this. So then you need to have also some kind of roughness, so that when you place the droplet on top, the roughness will actually enhance the hydrophobicity of the surface.
Okay, and how does that work?
So there are actually, if we go a little bit on the theory side, there you can the wettability can be divided into Wenzel state. So you have a droplet that is in Wenzel state, which means that you have that roughness on the surface. You place a drop there, and the contact angle can be, let's say, 150. But what happens is that still the water will actually penetrate into the roughness, so there will be no air pockets there.
So you need the air pockets.
You need the air pockets to achieve the superhydrophobicity, because at the Wenzel state, you don't really, if you measure the hysteresis on that type of a surface, you probably have higher hysteresis than the 10 degrees that I mentioned. So you actually want the droplets to be in what we called a Cassie-Baxter state.
Okay.
Which means that this just comes from the guys that have invented the theories. So then you basically have a water droplet on top of the roughness, so that you have air pockets in between. So actually the actual area where the water is touching at the surface is much less than the area of the drop.
Right.
So that's where the superhydrophobicity comes from.
Okay, so what about the roughness? Are there any requirements to make this happen?
Yes, so typically you would require what we call a dual scale roughness or roughness in two dimensions. So you typically have some type of a micrometer scale roughness. Let's say you would have some type of a pillar surface, for example.
So is that in like micrometer height
Micrometer
or width?
or both.
Or both.
Yeah, exactly. So then, so you would have like, let's say like 2 micrometer in diameter pillars. And then on top of that, you would have smaller roughness. So those pillars would be porous, for example.
Okay.
And the porosity of the dimensions of those bores should be less than 200 nanometers. So it has to be in nanometer scale then.
Okay.
So that's usually what you need to and I mean, of course, on top of that, you need the right surface chemistry. So you need to have the hydrophobic surface chemistry.
Okay. So, but then those values that you said, the 2 micrometers and 200 nanometers, are they give or take depending on chemistry and whatever drop you're putting on top?
Well, I mean, it's always water, of course, but then I mean, it's yeah, I mean, it doesn't have to be a pillar shape, for example. It can be like a pyramid shaped, but it's kind of that scale. So like one roughness is at the micrometer scale, and the other has to be in nanometer. In the scale.
And then you said something about the air pockets. So will the air pockets be on the micrometer scale then, or on the nanometer scale?
Well, typically I would say that probably nanometer scale, but they would be on basically kind of on top of the whole structure, ideally, so that it wouldn't penetrate at all.
In between the pillars?
In between, yeah, exactly.
Okay.
Yeah.
Okay. So we know there are natural materials, or we know the lotus leaves.
Yeah.
And we know what's required for them to be super hydrophobic. So can we make them?
Yes, we can. Yeah. So that has actually been kind of a very much research topic. I mean, if you look at the publications on the area, there has been numerous publications where people have been able to produce this type of roughness, I mean, super hydrophobic surfaces from various different materials. Typically, I would say you would have some kind of a relatively rigid substrate that you make the roughness first on that substrate, and then you coat that with the fluoropolymer coating to get the chemistry. So it's not so straightforward maybe to have a material that is kind of completely, I mean, the bulk material is already with the correct chemistry and the roughness. So typically you would fabricate the roughness and then coat it with something.
Okay, so what about commercial availability?
I mean, there are some, but it's quite difficult because if you think about how we produce them, it's typically done with some kind of an etching method, for example. So it's the scalability is an issue. So typically in publications you see them in very small areas. So they are like, let's say, centimeter times centimeter, or maybe like a wafer size. I mean, typically like silicon wafers are used. So that's one issue. But then the other issue is that since you have that roughness, it's quite difficult to make rough surfaces that can withstand all kinds of touching and whatever you whatever you have to do basically. I mean, if you think about where you could have on a smartphone on the glass, you might want that to be super hydrophobic, but people are touching it all the time, so the roughness will probably be destroyed, and then it's not really super hydrophobic then anymore after somebody has touched it.
Yes, exactly.
So the durability is really a big issue in this field, because it's where we want to apply this type of surfaces, they will most probably be touched.
Yeah, I'm thinking also
somehow.
like the raincoat that you mentioned.
Yeah.
In and out of your bag, and then it's like
I mean, it's so that's of course an issue. And then the coatings that we have to use, the fluoropolymer coating. So there has been quite a lot of attempts to get rid of that chemistry because it's not very environmental friendly to do the fluoropolymer coating. So people, there has been now a lot of publications where you have so that you could maybe achieve the superhydrophobicity with some other type of method than using the.
So is it the coating process or the coating itself that are not?
It's a fluoropolymer as such that
not good.
Yeah, exactly. So I think that's also something that is kind of we should have some other solution for that surface chemistry.
Maybe mimic the lotus leaf.
Yeah, that is definitely the starting point of the whole research.
No one ever tried it.
Yeah, now you invented it.
Okay, so I mean, some pretty tough challenges that you mentioned. Are we able to overcome those, you think? Or?
Yeah, I mean, there are already some products at the market. So there are some sprays that you can apply to the surfaces to make them super hydrophobic. But I haven't tested them, but I'm assuming that the durability is an issue with those. And
I guess you just have to refill.
Yeah, exactly.
From time
just
to time.
kind of exactly. So, but I mean that is already there are some available, but the market size is still very, very. Small, if you think the opportunities that could be there. But I think if you look at the research that is being done here, is that in the beginning it was enough if you just published a paper saying super hydrophobic surfaces made out of this material. That was kind of like, okay, well, new material, new technique to make the super hydrophobic surfaces, let's publish. Nowadays, I think it's not maybe enough anymore. I mean, because it's typically you have to kind of have something extra. So you need to, for example, one that people are very interested is kind of optical transparency. Of the super hydrophobic coating.
Why is that relevant?
Well, there are many applications where people want to use it, like in solar panels or solar cells, for example.
Windows,
of course. So you want to have so that there are a lot of examples. Then you could have, like for solar panels, anti-reflective coating,
right.
Because then of course you can improve the efficiency of the solar panel. So then you could have anti-reflective super hydrophobic coating, which would then make your solar panel more effective because of the anti-reflection property, but also because of the possibility to take the dirt, basically, the self-cleaning part of what super hydrophobicity gives.
Yes.
So that is absolutely, one thing that is that is quite interesting. And then a lot of publications on durability, so how to improve the durability of these surfaces. I think that's probably one of the biggest challenge here. So
how far are we there? Is there any hope?
I guess there's always hope, but it is a tough challenge since the roughness it's quite difficult to solve that. But all of these steps that are now being taken in publications are kind of steps towards the commercialization of these products.
So when do you think we will?
I don't know.
Hard to guess.
I don't want to guess anything. I don't want to be wrong.
10 years. It's always 10 years. Right?
Yeah, exactly. Yeah.
Super fascinating topic.
Really. This is, and we could also, I just want to mention, we don't need to talk about it, but we could go further and talk about super oleophobic surfaces.
Super oleophobic, and what is that?
surfaces that repel oil.
Repel oil. Okay.
That's even tougher, but that's also kind of the direction where the research is going. So there is a lot of things that people are researching around this.
We will save that for another episode.
Yeah, exactly. Yeah.
Okay, so that's what we had for this episode. So thank you for listening to me, Malin Edvardsson, and Susanna Laurén from Biolin Scientific. And I also want to take the opportunity to mention to those of you who are listening or watching that if you're interested in surface science and related phenomena, you should check out our blog, the Surface Science blog. Thank you.